Tim, you're going to show them. Excellent. Breathe defense.
那我就不要你。
那你就不要，你就那种吧，
就直接，
我就直接。
Press F11. Isn't it?
就这个痛。
No.
So, hello everyone. Today I'll have a thesis defense. So, my thesis will be divided in two parts. So the first part is the TRSFX study of simple antenna system in cryptochrome, and the second part is the preliminary study of time-resolved serial crystallography. So let's go to part one. So photosystem 2 is a membrane protein complex. So its function is to catalyze the light-induced water oxidation to process the photosynthesis. So in photosystem 2, there are a lot of LHC complex in the photosystem 2, and then in each of LHC complex there's a lot of antenna pigment bound to the reaction center. So the antenna pigment will be excited first after excited by photon, and then subsequently deliver the energy into the reaction center. So as you can see, the antenna system in the photosystem 2 is very complicated, and there also might have some chance to have different antenna pigment absorb the photon at the same time. So in photolayers, we also have antenna system. So and in the photolayers, antenna chromophore also will absorb the photon, and then it will transfer energy to the chromophore. So there's some antenna chromophore in photolayers like MTHF, HDF, FMN, and DMLR. So if we want to study the antenna system, photolayers is a good target because it is quite simple. So in my study, the target protein is crockery. Crockery is animal-like cryptochrome derived from Chlamydomonas reinhardti. So crockery is a bifunctional protein. So it has the function of photolysis. So it can have the function of photoreceptor. It can regulate the circadian rhythm and sexual life cycle. And on the other hand, it also has the function of cryptochrome, so it can catalyze the repair of 6-photo photo product. So as I just mentioned, HDF is one of the antenna chromophore. So it is the antenna chromophore of crockery. So in crockery, the the chromophore FAD and the antenna chromophore AHDF, the distance between those two is around 17 angstrom, and their extinction coefficient is about so AHDF is 3-4 stronger. So which means that it has high opportunity, a high chance to have the double excited, so i.e. the multi-photon absorbed at the same time. So Crockery is a good target to study the antenna system due to this reason. So in our previous study in our lab, Yuhei and Nigel did the TRSFX experiment on the crockery without AHDF. So this is the oxidized state FAD, the dark state. So after photo reduction by blue light, crockery will process the electron transferring pathway to shoot the photon to FAD to become FAD dot minus, and after in microsecond time scale, there's another proton transfer pathway. So
we know that that's not the case. Well, are you reading that from Nigel's thesis?
No,
From where?
it's not the.
Hundreds of milliseconds.
You mean the proton transfer?
Yes.
Yeah.
Tens to
Yeah, it's
hundreds of
in milliseconds. Sorry.
It's because in Nigel's thesis, because of the way that everything was moving, our operating hypothesis at the time was that actually the movement of the solid exposed patch was what was initiating the proton transfer.
Yeah.
Now, based on the what they call on the TRI, because we know that it's actually the release, the reversion to the original state, which actually represents the protonation. Okay, so that's why if you read Nigel's thesis, you will read that we believe that the protonation takes place in microseconds.
Yeah.
While it is not the case, it takes place in tens of milliseconds to hundreds of milliseconds.
What I know is the protonation initiate at microsecond time scale, but the real protonation transfer is around 100 milliseconds, right?
Okay, but you have to be careful there.
Yeah. Okay.
And again, it's not your fault. It's just our internal sources have changed over time, isn't it? So
after knowing the mechanism of electron transfer pathway and proton transfer pathway, we want to study crockery in the presence of AHDF, so that we can know how does antenna chromophore affect the reaction.
I think here, well, I'll continue. Okay, let me see if you have it or not. Okay, you don't. You should cite Yuhei's paper and describe it.
Okay.
Because that's the paper where Yuhei showed that, at least for the reoxidation, there's a clear difference between the presence or absence of the 8-HDF, and that therefore there's good reason to believe that the photochemistry, or not only the photochemistry, but also the protonation dynamics of crockery may be affected by the presence or absence of 8-HDF. That is why it's not just like, oh, do you know what, we were bored and we have all of this protein, we have some 8-HDF, why don't we throw the protein on the 8-HDF to see what happens? Do you know, we actually did have a very good reason
Yep.
to want to study that.
So it's the 2023 paper, right?
Yeah. That's why I'm saying this is the thing is that when we were doing this, obviously the paper was not published, but Yuhei did exist, so he could tell us that. You know what I mean? So that's why we could work directly on this type of experiment. So that's why you need to keep that. I mean, in your introduction, you should make some space for that one because that's your motivation.
Yeah. Okay, so we performed the TRSFX experiment in Sekala. So the TRSFX experiment setup is to use the laser pulse, so the blue light laser pulse.
Sorry, I'm going to interrupt you again on this one. Just a small thing. Call it pump. Because you see, actually at some point, because I find it quite similar, there is a short story written by a South American writer called Instructions to Walk Up the Stairs. And so the whole point, it's a comedy, a short story, which is basically a set of instructions about how to walk up the stairs. But he doesn't make the difference between left and right foot. So he just goes, take the foot and put the foot in front of the foot. And then continue with the foot on the foot on the foot. And do not raise your both feet at the same time, because if not, you will fall down. And so you see, you're in a bit of a similar situation where the expel is a laser, and the pump laser is also a laser. So you first shoot the laser to then shoot the laser, with one laser being at 15 hertz and the other laser being at 30 hertz. So the word laser is not a particularly good word to define what each of them means. You see what I mean? So X-ray is pretty good. So you could call it optical laser. Okay, so as a visible laser. So visible light laser. You could call it pump laser. Yeah, and then you call the other one the X-ray probe, for example. Okay. Yeah. Something like that, but just make it a bit easier to. I mean, for us it's not a problem, but if you're going to present in front of people who don't know, they're going to be like, okay, so wasn't the X-ray a laser? Why do you have two lasers? What the hell is happening? So.
Okay. So we use 405 nanometer blue light pump laser to photo reduce our crystal. So after a certain time delay, we use X-ray pulse to collect the data, so that we can get the light structure after the illumination. And yeah. Okay, so this is the dark structure that I refined for the Crockery dark data, and we so we have 8 time points. We have 8 light structure in 10 nanosecond, 100 nanosecond, 300 nanosecond, 1 microsecond, 3 microsecond, 10 microsecond, 1 millisecond, and 3 millisecond.
Back there, because you can brag, write the resolution.
Okay.
Yeah, because I mean, you're what, at 1.3, something like that?
The dark data, is 1.37.
So you have proper atomic resolution, isn't it? And you're below the van der Waals diameter. That means that you can tell the difference between individual atoms in your structure. And so that is, remember the first question, or one of the questions we asked SAP was, what's the resolution? Because you're seeing movement of 0.5 angstrom and so on. Well, if you show me some movement of 0.5 angstrom at 1.3 angstrom resolution, I believe you. You see what I mean? Okay. So that's why I think again, just make your case stronger when you show the information.
Okay. So, in the light structure, there's some region with stronger signal that we are interested. So the first region is the C-terminal region, and another region is around two binding pocket of chromophore and antenna chromophore. So the second region is FAD binding site, so which is the region that we saw the proton transfer pathway in the quark-free without HDF structure, and the other region is HDF binding site, and it also has some. There's also some important residue that recognize the HDF, and the last one, but it's the most important one, is the Q390. So in my structure, Q390 have a special double conformation. So let's see how it behaves. So let's first focus on this two binding pocket. Okay. So in the dark.
Sorry, Tim.
Yep.
Another thing here about the color choice. It looks great. I actually prefer red and green. But the reason why you will almost never see it is because most people in the field are men. There is a pretty high chance of having colorblind.
Yeah, I know.
For example, Jörg Stadfuss is colorblind.
Oh.
And that's why that was the main reason why we changed the color. I used to present everything in green and red, and then when I showed him the data for the MMCP2, the DNA repair, he was like, "Yeah, this looks great, but I cannot tell what is what, so please change the colors." So, considering that it's one of the reviewers, I mean, they will probably be one of the reviewers for this, and this is something that it will be there. I mean, the kind of story that we have here will probably present, sadly, mostly men. For once, they have a disadvantage, isn't it? So that's colorblind, so help them. Okay, that's why magenta cyan is easy to tell the difference for colorblind people, and gold, so yellow and blue, is also easy for them to tell the difference. That's why you will see those two combinations being sort of the more common ones.
Yeah, I know I should use that color, but I don't have that much time for
No worries. I'm just saying that keep that in mind. Okay.
Okay. So in Q390, in the dark structure, there's already have two conformation, and the occupancy is about half and half. So this is the DFO map. So as we can see, the A conformation, the occupancy of A conformation decreasing, and the B conformation occupancy increasing. So the decreasing and increasing is until 1 to 3 microsecond, and it's around to 3 millisecond is around the same. So here I also integrate the negative density of conformational A. So as we can see, the maximum negative value is around 3 microsecond, and the tau is 0.7 microsecond. So there's also there's another water here, so it's close to conformational B. So as we can see in the integration density, so we can see they have very similar kinetics. So both of them with tau around 0.7 microsecond. So which means that the localize of this water is because of the increasing of the Q390 conformational B.
They're coupled.
Yeah, they are coupled. And so we can know that the this water delocalized and the Q390 conformational B occupies more gradually until 1 microsecond to 3 microsecond.
I think here in that figure, you could write the direction of FAD and the direction of 8HDF. I think it will allow people to orient themselves, and also, of course, for your story, it's quite interesting, isn't it? So basically, the A conformation points towards the FAD, if I remember correctly. The B conformation towards the 8HDF. So as it gets illuminated, it's equally sort of divided, and we see a movement towards the 8HDF, so which I think is quite interesting. I'm just again small things, okay.
Okay. So to estimate the occupancy of Q390, the two conformation of Q390, first we use the extrapolation. So why we need to use the extrapolation is because when our crystal sample after the crystal sample illuminate, because of the crystal size and the extinction coefficient, not extinction, I
mean, that's why this is not true for us. This is true if you work with bacteriorhodopsin.
You mean we should have more red color?
The point is with bacteriorhodopsin, you only get about a 3 micrometer penetration into the crystal, because it has such a high extinction coefficient that it just penetrates very, very little. So which means that if you're not careful with it is in fact true that you have the where you shoot with the X-ray, it may be one part that has a very high concentration and another part that has very low, because the extinction is very, as I said, the extinction decrease, or the extinction, the excitation decrease is very sharp. Okay, so this is a significant component for bacteriorhodopsin. In our case, we have about a 10-fold lower excitation coefficient, even with 8HDF. And so by doing that, what that means is that actually, well, I would have to calculate it, but without 8HDF, the penetration was about 500 micrometers.
500.
So penetration is measured as the 1 over epsilon, 1 over E, what's called transmittance. So that means 1 over E transmitter is 37% transmittance. So you tell it how long does the beam need to travel through this crystal to get to a transmittance of 37%. And if I remember correctly, for Cracker it was something like 400 micrometers or something like that. So that means you would have to have a crystal that is 400 micrometers thick to lose at least 37% of. I know with 8HDF you have a much higher excitation coefficient. We should calculate it, okay? But if I remember correctly, it is not high enough to really affect your crystals, because you remember your crystals are roughly 50 micrometers by 10 or so, isn't it? So because of the flow, you're normally going to be looking at the 10 micrometer side. So in your case, it's mostly what you're showing on the second part. That is, that in the crystal lattice, due to the quantum yield of say 20% or so, even if everything absorbs a photon, after that, not everything will initiate the reaction. This is the opposite problem that you have with bacteriorhodopsin. Bacteriorhodopsin has a quantum yield of something like 89% or something like that. So if you get it to absorb a photon, almost every single molecule will actually initiate the reaction. So your main concern is that you have crystals that are small enough that they can be penetrated as much as possible. In our case, we have the opposite situation where penetration is not a problem. We can penetrate it even any way we want, but relatively few of the excited molecules will actually proceed to initiate the actual reaction. You see? Mm-hmm. So it's a problem of quantum yield in our case.
Yeah.
Okay?
Okay. So what we collect from the light data is it will be like the mixture of ground state and trigger state. So by doing the extrapolate, we can get the fully trigger state data set. So we can get the true light data, true light structure. So to do the extrapolation, we use the method called an estimation. So this is how we estimate the n value here. So as we can see, the 10 nanosecond Q390 is the n equals 22, and to 1 microsecond is around 7 or 8, and so
I think this one, same thing I told Kevin. I would just leave the upper part and explain that you're using.
Okay.
Do you know? Because the problem is that when you have the lower part, and I would not call it N estimation, but occupancy estimation. Okay. First of all, because now you need to explain what N means.
Yep.
Then you need to explain what you're plotting there.
Mm.
Which means that then you're going to have to explain what an extrapolated map is, an extrapolated residual map is.
Mm.
And so all of a sudden you're spending 15 minutes on this slide for not much gain, isn't it?
Mm-hmm.
I'm saying for your defense.
Yep.
You can have it as a supplementary slide.
Mm-hmm.
If someone asks, oh, so you mentioned that you estimate occupancy, how do you do that?
Mm-hmm.
And then you can go into detail.
Okay.
But I would not have it as a main slide, because I think it completely deviates. Same thing I told you, it completely deviates from the story that you want to tell. It's a very important technical detail, but it is not necessarily what you want to have in your presentation. You see what I mean?
Yep. Okay. So I used two different methods to calculate the trigger state occupancy on specific residue. So here is Q390. So the first method is use this formula to calculate the to use the n value to calculate the trigger state occupancy. And the second method is to use to create the map from the mixture raw data. So we can calculate the trigger state occupancy by observing the peaks of the trigger state and the should be trigger position and dark position. So from these two methods, I can get the very similar occupancy curve. So in occupancy after I get the trigger state occupancy, I also can found that the conformational B occupied until the increasing is until 1 microsecond to 3 microsecond. So it's the same time scale in as what we see in the DFO map. So next is the FAD binding site. So there are several residues that we are interested in. So the first one, of course, is the chromophore FAD, and the other one is the N395, which is next to FAD, and the E384 and H309. And there's also some water around this region will be delocalized after the illumination. So because this is only the DFO map, so later I will show you the DFO CC result and check the DFO map together. And this is around the HDF binding site. So I just mentioned that there are some residue can recognize HDF. So like lysine 258 and the tyrosine 49. And there's also some residue will recognize HDF around it, but we only can see the movement on tyrosine 49 and lysine 258. So to refine the structural change, first we do the correlation coefficient of DFO maps. So we calculate the if we want to check how the correlation coefficient between different DFO maps around lysine 258. So we just focus on this region, the negative, the signal that we are interested in. Then we calculate the correlation coefficient and plot them like this kind of heat map. So this method is the script is provided from Tom. Yeah. So to check the similarity of the DFO signal, so to having the correlation coefficient is to check how's the similarity between the different time points of DFO signal. So if the CC values are higher, which means that the conformational change are closer. So like in this map, this plot, we can see that maybe from 10 nanosecond to 1 millisecond, they have higher correlation coefficient. So maybe their conformational change is closer, and like in 3 millisecond, probably it has its own conformation. So after we create this map, we do the DFO CC refinement. So we generate the candidate model by Python, and then we calculate the CC value between the DFO and DFC, and then we repeat the step until we get the highest CC value converge. So here's my correlation coefficient map. So like in FAD, so 3 milliseconds looks like it has its own conformation, and D321 probably 10 nanosecond. But like in N395, because the correlation coefficient is a bit low, it's probably because of some noise around it, so we cannot really find the find a better group. So so by using this, we design our DFOCC refinement strategy. So first we separate the time point into different group based on the correlation coefficient map. So like in FAD, as we see, there's two groups. So in the first group, we take the one with the highest occupancy and run the full DFOCC refinement step. And the other group also we take the highest occupancy one. Then after we finish this round of DFOCC, we use this model to run the smaller range DFOCC refinement on it. So by this method, we can make DFOCC more efficient. So here's my DFOCC coordinate. So FAD is like the X and Y translation, and four different like bending, yeah. And so for D321, because in DFO map we can see that the positive signal is big, so probably it has double confirmation. So we perform both single confirmation and double confirmation, and also we can have the occupancy refinement on double confirmation. And also, so there's another DFOCC refinement. So for Q390, what we did is only we want to refine the occupancy. So here's the CC value for all of the DFOCC result. So Q390, there is some problem. So
that's the most
yeah.
important one, isn't it?
Yeah.
What happened there?
So the problem is because like maybe like from 60% occupancy to 80% occupancy, they have same CC value. So but what we can get for CC value is how to say that for
significant factor.
Oh, so you only see it on like the fourth or fifth significant digit.
Yeah.
Oh wow. Okay.
So maybe that's the problem.
Yeah, but that's not surprising. It's not surprising, in the sense that the CC. Remember that this is do you know what you could do? You could do beta maps. This is where the beta maps actually would work. Dr. Kilo.
Okay.
So you see. So because the issue here is going to be to reproduce. So you see, your problem is of course that if you have the correlation coefficient doesn't care about the slope.
Mm-hmm.
So let us imagine that you have a value. Okay. What happens with occupancy? With the difference in occupancy? What happens with the difference in occupancy is that you're going to get some values that are going to be 1 that are now 2, isn't it? And some values that used to be 1 that are now 0. You see what I mean? So your problem is that, let me if you don't mind, let me draw it, okay? Because I think that's kind of I think I understand the issue. Sorry, I did not think about this before, but I see that this is not necessarily it. If you don't have like important conformational changes, this is going to be an issue. So, we're back to this. So, okay. You see, let's imagine, okay, that our x-axis is our actual data, isn't it? And so that means that you're going to get values that are going to be somewhere positive, isn't it? Mm-hmm. And some negative, isn't it? If this is our 0, this is data model, isn't it? Like this. Okay, so now the issue is the following, okay? Let us imagine now that you have one set of occupancies, let's say 30%, okay? That means that, for example, some values that used to be positive, okay, here they will also be modeled as positive, isn't it? Now, if 30% is too high, what will happen is that it will not be in this position. Or let's, great, no, it doesn't work. Do we have another one? Let's see. This one? Nope. This one? Yeah, this one works, at least for the moment. Okay, now let us start with the perfect occupancy. So if this one has this value, we should find one here with exactly the same value, isn't it? So we will have it here. If this one has this value, we should find one exactly in the same place with the same value, isn't it? If this one has this value, we should find one exactly in the same place here with the same value, isn't it? Same thing here. If this one has this value, we should find the exact same here, isn't it? So that means that we can draw a line like this, which will have a CC of 1, because remember, CC equals R squared, so the root of R squared. Okay? So it will have a CC of 1, okay, and also will have a slope of 1, isn't it? So now let's imagine that we overestimate the occupancies by a factor of 2, so that everything is in the model is twice as much as in the what's called in the structure, isn't it? I mean, since I don't have a different color, I'm going to draw again the coordinate. Okay, and so now here we have our actual values, isn't it? And here we have our coordinate axis. Okay, so that means that if we now have a value here, we would expect to find it here. If we have a value here, we expect to find it here. If we have a value here, we expect to find it here. And if we have a value here, we expect to find it here. So now we can draw a line. What will the CC be of that line? Still 1. Okay? Because the line fits perfectly. However, what will be the difference? Slope will be 2. So, how do you determine the real occupancy? You determine it by finding the correlation plot that has a slope of 1. Mm-hmm. Then you have the real, which is a beta map. Do you remember? Mm-hmm. Okay? So if you do correlations of the, if you do a correlation between observed and calculated beta maps, probably then you will find the actual concentration, or you can just do it like this, just plot one versus the other and calculate the slope. Do you know what I mean? Plot the integrated densities. I mean, then calculate the slope from the integrated densities. Okay. You see, obviously, your first step should be to find the highest CC, isn't it? And so once you have found a subset where you're saying you have them on the 4th significant digit or something like that, At that point, I would do this kind of plot, and the one that produces a value of 1, or the closest to a value of 1, that's your real occupancy. Okay?
Mm-hmm.
And that's what I would do.
But I think for the beta map, what they did is the voxel-wise.
Yeah, they are comparing
Different maps.
Yeah.
And they're calculating the slope between different regions of the map, isn't it?
Yeah.
So what I mean is that you could do a beta map of the calculated versus observed.
Yeah.
Mm-hmm.
Yeah.
You see what I mean? And whenever you find that the values around the what's it called, the glutamine are 1, then you have the right occupancy.
Mm-hmm.
Whenever the comparison between FO minus FC produces values of 1 in that area, what you have is the actual occupancy, because remember, the beta is the slope of the correlation map. You see what I mean? So this is, again, I think this is simpler, just to do this.
Oh.
You see what I mean? So you just get all of either way, you already have the values, don't you? I mean, the integrated density values. So you already have all the integrated density values. So you just have to plot one versus the other. That's what you're doing when you're doing correlation coefficient. What you're doing is basically that. I mean, you don't really need to plot it. What I mean is that if you're doing correlation coefficient, by definition, you have done a linear regression.
Yeah.
So you just need to extract the slope of that linear regression. You see? Good?
Then the FAD still running,
Yep.
and for H309 we can see the CC is a bit low, but I think in the map it still looks reasonable.
Well, we'll take a look. Yeah. It's something, because 0.2 something.
Okay. Okay.
Maybe you're having an issue either with the region that you're
Yeah,
probing,
maybe.
or basically that the H309 may not be moving. If I remember correctly, there was an issue there where water appeared to be more important. So you can take a look, because don't worry too much with it.
Okay.
That may be.
So here's the DFO C3 refinement around the FAD binding site. So here the FAD light structure what I use is all of them is the 10 nanosecond one.
Mhm.
So in the first time point 10 nanosecond, we can see the FAD is already have signal which is the FAD react to FAD dot minus in picosecond time scale. Then in 10 nanosecond, we can also see that the N395 is like tilt a bit. So the nitrogen didn't move, but the oxygen moved a bit. So this is so the N395 this tilting behavior is from 10 nanosecond to 1 microsecond, which is different from Crockery without AHDF. So in Crockery without AHDF, we can see that the N395 rotate by 90 degrees from 10 nanosecond.
Yep.
So from 10 nanosecond and to 300 nanosecond, the structural change is more or less the same. Then to around 1 microsecond to 3 microsecond, we can see that because what I mentioned that water 460 and Q390 is almost fully delocalized, and the B conformation is full occupied. So after this time point, we can start see some proton transfer signal. So in 3 microseconds, we can see that the N395 rotate by 90 degree, and the E380, because of N395 rotate by 90 degrees, so the E384 have some space to go into here and replace the water. And also the maybe it's because of the broken of the hydrogen bond network, so another water here is also disappeared, so the H309 can go to this place. So until 3 milliseconds is more or less the same. Yeah. And here's the DFOC refinement result of HDF binding site. So from 10 nanoseconds to 1 microsecond, there's we can see that the water 460 fully delocalized. Then we can start see the signal, the different signal around lysine 258 and tyrosine 49. Yeah. So we can see that the lysine move from here to here, so it's a bit closer to the hydroxyl group of HDF. And for the tyrosine 49, because the movement is a bit complicated and is related to the main chain, so maybe later I will use the extrapolate. I'll try to refine against the extrapolate structure factor. Yeah. So let's see the interaction in two binding pockets. So in the dark structure, we can see that there's two water around here, so it's recognized by N395, and probably these two water have the hydrogen bond between them. Then in the second pocket, there's two water, and they have the hydrogen bond network with tyrosine. So if this region is hydrogen bond network, so maybe it's reasonable, because this hydroxyl group and this hydroxyl group have the reasonable distance, and the lysine here, the nitrogen, have the reasonable distance. So which means that HDF is in the protonated state in the dark. And if this cation and anion is sub-bridge, which means that in the dark HDF is in the deprotonated state. So there's two different interpretation. And in the 3 microsecond structure, we can see that because these two water delocalized, so E384 4 can go to here, so have the hydrogen bond with the rotated N395. But the interesting thing is here, the lysine is getting closer to the hydroxyl group here. So the distance between these two is getting closer, so which means that it is not the reasonable distance for hydrogen bond. So it could be the salt bridge. So if this is true, which means that we can see the HDF deprotonation here.
Again, I'm not quite sure if I would agree with you that that's a salt bridge.
You mean too short?
Well, in general, in a hydrophobic environment, which is where you are, salt bridges can be very long. Remember that a salt bridge's strength depends quadratically on the distance between the two ions and on the dielectric constant of the medium. The dielectric constant of what's called hydrophobic environment is much higher than that of water. So that means that salt bridges in hydrophobic environments are much stronger than in hydrophilic environments. So that means that generally in a hydrophobic environment you can see a salt bridge even if the two elements are far away. Maybe 4 or 5 angstroms away, you can still have a salt bridge because the dielectric constant is so low that the neutralization between the two, the anion and the cation and the cation, can still happen. As we discussed, I would be thinking about how the proton is being shared. I think that under that condition, the proton is being shared much more equally. So in the 3 microsecond state, the proton of the lysine is being shared much more equally between the lysine and the oxygen, compared to the situation in the dark state. Also, I think that you also need to check, because I get the impression that that side is much more likely to be making a hydrogen bond than that side.
You mean
So-
this side and this side?
I mean the lysine and the 8-HDF. So the lysine and remember that the hydrogen bonds have 2 components. One is the distance, the other is the geometry. And generally, what you want from the geometry is, since you cannot see the hydrogen, but what you want is the hydrogen bond donor to look like this. The hydrogens should be here, and the hydrogen bond acceptor should be here.
Yep.
So you expect this kind of about 120 degree thingy like this, isn't it? But there I get the feeling that one is pointing at, so if this is the 8-HDF in the dark, the lysine is pointing like this.
Yeah.
You see? So if that is the case, that is much more likely to be a salt bridge than a hydrogen bond. Because remember, a salt bridge doesn't need to be conducted by anything. That means a salt bridge is 2 fields, a positive field and a negative field, that overlap with each other. And as a result, they can overlap without any kind of orientational preference, isn't it? So as long as they're close by, they can have a dipole-dipole interaction, so a permanent dipole interaction, or directly a plus-minus interaction, an anion-cation interaction. Meanwhile, the other one, I get much more the feeling that the lysine goes from this orientation to this orientation. So I feel that the second one is much more likely to be both a salt bridge, because it's an interaction between an anion and a cation, and a hydrogen bond. So because the interaction might be the correct one, and a hydrogen bond where the hydrogen may be shared quite equally, so that it is not clear under those conditions which one is the hydrogen bond donor and which one is the acceptor. And as a result, you would have, instead of having lysine plus and oxygen minus, you would have oxygen minus 1/2 and lysine plus 1/2. You see what I mean? So I'm saying that just from the structural point of view, this is how it feels to me. Yeah? Yeah.
So
I think this is something that we can definitely, I mean, perhaps you can think, I'm thinking maybe we can do a bit of, because in this case, we just need to define the 8HDF as having a negative charge there. So perhaps what's it called, constant pH simulation or something like that, forcing the two to exist, introducing a harmonic restraint that keeps them in within 2 angstroms from each other, or not, and see how that affects the what's it called, the pKa of the lysine and the pKa of the, well, you're not going to be able to calculate the pKa of the thingamajig of the 8HDF, but you will be able to calculate the pKa of the lysine. And if the lysine all of a sudden becomes much more acidic by being in that orientation, that could already be an interesting feature, isn't it? So, you see what I mean? So, I mean, I think it's a really good analysis, and I think that this is really important, that this is a key discovery that you have made. I would suggest that you try to put it more in the context, I mean, think of structure and so on. Try to analyze it a bit more rigorously based on what you have. Do you know what I mean? So the kind of structures that you have and so on.
So what I think is there's maybe one problem here, because the difference, this difference map peak is only at the nitrogen atom. So because what I did on DFOCC is the whole section.
Yes,
so probably there's some issue.
In what sense? No, I would do the entire side chain, but I would probably just cut it off around the nitrogen.
Mm-hmm.
So what's your CC half? What's your CC on it? Yeah, I would be a bit careful with that. My suggestion is that you take only the nitrogen for so that you only move the nitrogen. Yeah, you're right. Probably you want to move the nitrogen and maybe the previous carbon or something. Do you know what I mean? And then redo it just with that and having a very narrow range. The issue with lysines is that basically the bottom bar, they're so long that they can adopt whatever conformation we wanted to adopt. And basically in the tube that you're going to have in your density, whether they're, how should I say, or not much of a difference. You know what I mean? That region you're, but yeah, I think that maybe you need to do it maybe with, what is it, the nitrogen epsilon, is it? Nitrogen gamma or nitrogen epsilon? Epsilon, is that it? Yeah. Nitrogen epsilon and gamma carbon.
Okay.
And see by still doing the refinement on those two, see what you can get. And also making the box only in that region. Do you know what I mean? Because my guess is there that you have quite a bit is sort of hidden behind the having had such a big box, isn't it?
Yeah. Okay. Okay. So the last one is C-terminal region.
Yeah.
So it is the older version.
Yeah.
So as we can see here, because the proton coupling electron transfer is happen before 10 nanosecond, so we can see that the signal is
already there.
Yeah, it's around almost saturate at 10 nanosecond. And then for the C-terminal helix, we can see that from 1 microsecond they start have some negative signal until 1 millisecond. It has the largest signal here. So this signal is suggested to be the unfolding of the helix. So in my my data query with HDF, the tau of unfolding is around 7.4 microsecond, and in query without HDF is 47.8 microsecond. So we can see that the C-terminal helix unfolding is faster in the presence of HDF.
I would like to ask you there,
Hmm.
do me a favor, just add the 1 millisecond time point, the value of 1 millisecond,
Uh-huh.
added at 100 microseconds.
Added to 100 microseconds.
Exactly. Or put it basically take the value of 1 millisecond and set it at 100 microseconds,
Uh-huh.
and then take 10 microseconds and 1 millisecond,
Uh-huh.
average the two values,
Uh-huh.
and put it in the position of
Ah.
100 microseconds.
Probably
And tell me the
here,
difference
here.
in tau.
Okay.
My point is that sadly, I think you cannot say this. Why? Because you need to have data points close to the saddle point. You see what I mean? And so you want to have one that is close behind it and close in front of it. If the 100 microsecond time point has a value which is between 10 and 1, between the value of 10 microseconds and the value of 1 millisecond, then your tau is going to be similar to UK's. If, however, it has a value close to 1 millisecond, then the value is going to be similar to your own. You see what I mean?
Yeah.
So that's why I'm a bit worried about that one. I do believe, though, that it's a bit faster. I think that it can be argumented also with the densities, isn't it? I mean, the occupancy is about the same, isn't it?
I haven't checked. I
You
haven't
should check
did
if the occupancy is about the same, because if the occupancy is about the same, the value, the integration or the integrated density value should be about the same. So you can tell me that the value for 100 microseconds is reached. So let's see. Yeah, I mean the values in 1 millisecond are
it's
very
around
similar,
the same.
isn't it? It's about -12 in
Mhm.
both cases, isn't it?
Yeah.
Yeah. So then let's, for example, take a look at the value of 10 microseconds. That's about -7 or so. And there it's there it's going to be much higher.
Yeah.
You see, in 10
Mhm.
microseconds, it's about -7 or so. And based on that prediction, the 10 microsecond here should be about -5 or so, isn't it? I mean, in your case, it's actually it's close to 0. So, yeah, I think you can make. I would rather than. I mean, you can say that you've calculated the tau as being 7 point something, 7.5 microseconds, but I would highlight that, based on the data that you have, the negative, the density really does accumulate much faster. If we compare point to point, we can see that the initial points are lower in your case, so the density has accumulated much faster. And not only that, but there is also the points in the end are also reaching similar level, which means that you probably have a similar occupancy. Yeah, so that's where I would go with it.
Okay.
So, continue. Let's see.
Okay. So the conclusion of the first part for this story. So in the presence of HDF, we can see that the mechanism is quite different in the between the quackery, and I think the most important thing in my story is Q390 play an important role to initiate the proton transfer pathway. So it decreases in one conformation and increasing in the other conformation. And I think that it is like a switch between chromophore and antenna chromophore. Yeah. And the other interesting question, maybe maybe you can run the.
I think it would be nice to
simulation.
run those simulations.
Yeah.
See, I mean, in the 3 microsecond states or something like that, after you have re-refined it. I don't want you to have to do 3 million versions of the same simulation because we don't have a reasonable structure. But yeah, I think that would make sense. And also, I think, I mean, that I think would be very good. Yeah, I think that's good. And I'm still intrigued with the tyrosine, because you mentioned you had some trouble with the tyrosine. You couldn't display the map correctly there.
Actually, because it's only that the problem is that I think I didn't import the map into the PyMo correctly, so I have the cutting by the unit cell.
I know. Yeah, but that's okay.
Okay.
Okay. So
the part 2, quickly go through it. Okay, the preliminary study of TRSX. So the first part will be UV-induced cyclobutane pyrimidine dimer formation. So as we know, there's a lot of agent could cause the DNA damage. So one of them is the UV radiation. So it will cause the DNA to form the 6,4 product or cyclobutane pyrimidine dimer, and so in order to repair the damage, we use an ER. So if people cannot repair the UV damage in DNA, it will cause the disease called xeroderma pigmentosa. So what we want to study here is how the DNA damage the cyclobutane pyrimidine dimer form. So because in our previous study we have already known that the mechanism of the photolysis catalyzed repair of CPD. So now we want to take a look at the DNA damage part, the opposite way. Okay. So in the time result IR spectroscopy, they can find that the CPD dimer are fully formed around 1 picosecond after the UV excitation. But however, there's still another study debate around the structure of the reaction intermediate. So here, TRSFX is a powerful technology to capture the CPD formation in ultra-fast timescale. So what I have did is to try to crystallize the DNA and screening and have the optimization of the crystal. So the method I use is hanging drop, and I've tried 3 different DNA and 29 conditions from nucleic acid database. So after trying to get the better condition, I optimize them, and I can get a lot of single crystal. So this is my final condition here, and the crystal was growth after 14 days, and I've tried to crush the crystal. And why I want to crush the crystal because is that we also try to use UV lamp to illuminate it and want to see is there any DNA damage on it. So after I crush them, the crystal look like this, and this is how it looks on the squeeze loop. So the crystal size is like around 50 micrometer to 100 micrometer. Yeah, so I can get the DNA dark structure with the resolution 1.7, and yeah, I think I still need to spend some time on refining this structure. Yeah, and but I mentioned that we try to illuminate the crystal by UV lamp, but somehow the crystal the result cannot be indexed properly. So we still finding the way to get the proper unit cell, and the work it will be progressed by Zach. Yeah. So we have also tested the sample in Swiss field. So we mix the DNA crystal with grease. So here's the how's the crystal looks like in the grease, and we successfully run the sample in the injector, and we can actually see some diffraction here, but it's not very clear.
Yeah, you should, for that, you really need to exaggerate it. To show it on a slide, you should open it with like Photoshop or GIMP or something like that, and just crank up the contrast. You know what I mean? It looks horrible on your screen, but it's the only way to show it on a
projector.
What's called on a beamer, because what's called projectors have such low contrast that you see nothing.
Yeah. But I want to find a better pattern. But
Next one. Yeah.
but the Chris field in Swiss field cannot.
Okay. Well, we will see. I'll call them. See what we can do.
Okay. So
They have the opposite problem as the Japanese, don't they? Well, in Sakla, the problem was that what's his name? What's his name? One the really good guy that set up the pipeline and so on. And then went to Oxford to cryo. Nakane, yes, sorry. So Nakane left, and Sakla was left at Criswell 0.6.2 for like 5 years. Nakane returned, and then it was updated. You know? And so the issue with Sakla for a while was that they were using very old Criswell software, and so you were losing quite a lot of images that with a more modern version of Criswell you could actually get because of the improvement of the algorithms and so on. But you know, at the same time, you want a certain stability. It cannot be that every 6 months they're installing a new version of Criswell, and now all of a sudden the old data doesn't work anymore with the processing environment they have. Like, that just doesn't make any sense. Okay, well, whatever. Okay, then intermolecular movement.
Yep.
Let's
So
see.
the second project for the TRSX is the intramolecular movement among the module of non-ribosomal peptide synthetase. So non-ribosomal peptide synthetase is a modular multi-domain enzyme. So each module always contains adenylation A domain, alylation T domain, and condensation C domain. So A domain here, A domain will recognize the amino acid and activate the amino acid by adenylation, and then it will transfer to the downstream T domain. So the T domain will use the sial group to connect the adenylation amino acid. So, and then the C domain will catalyze the formation of the amide bond between amino acid and peptide in the neighboring T domain, and elongate the non-ribosomal peptide. Yeah. So because the NRPS the movement in the NRPS among the different modules is very huge. So we think that it is it is a very interesting target to do the time resolved crystallography. So the strategy of capturing the movement intermediate is to first wait, here's my photo cage.
Yeah.
So
Imagine there is a big ball.
Yeah. So first we bind the attenuation AMP with the photo cage on the NRPS A domain, and then after we illuminate by pump laser, then the photo cage will leave, and then it can initiate the movement will initiate. So we can use time resolved serial millisecond crystallography to observe the movement.
Yep.
Oh, here.
Okay.
Okay, so this is our module from Jiangsu step. So we do the crystallization by the robot and try around 3,000 conditions from the kit, and then we found one condition can diffract, and then we try to optimize this condition and found that there's a plate crystal, and then we use this crystal to do the seeding, and then we can get a lot of microcrystal in this condition.
Fantastic.
So this is the NRPS structure that I refined until now. So as we can see that we lost the N-terminal T domain and the C-terminal T domain. So it probably because of what I just mentioned, the movement between among the NRPS complex is very big. So it will so between the module there must be a very flexible loop. So maybe that's why the T domain is disappeared in the structure. So we want to either remove one T domain or binding some substrate to make it more fixed. Yeah. So this project will go to kilos. Yeah. Okay. And thanks for your attention. Yeah.
Very well done. I have to leave in a moment, but before I do so, let me give you sort of my pointers on it. I think you really need to go back to Yuhei's manuscript. Okay? Either at the beginning or at the end, you need to do a sensible comparison to it to highlight where are the differences. Do you know, because I don't know if for you guys it was the same. I know the mechanism quite well and so on, and so I could follow. But I think if I would have known it, it might have been quite difficult. You said, oh, you see, this behaves differently. If I wouldn't know what you mean by differently, I would be thinking, different from what? Do you know what I mean? Like, so I think that's definitely something you need to work a bit on. So how to incorporate that into the presentation to make it, to give a bit better of a framework. I think also that you spend too much time looking at those general figures with all the density maps and so on. These figures are not very easy to see. I suggest that you say that you spend, if you want to impress people by saying, see, 8 structure, and look at this, amazing. do it, but get rid of those figures quickly.
Mm.
You know what I mean? Now, we did 8 structures, and see, here we can see something. But the key point where we see this is on this one. And then you click again on your slide, and then you make a zoom on the one figure that you want to discuss. Do you know what I mean? So, for example, if we were talking about the lysine there, what was it, 3 microseconds, isn't it? So you go, see here, down here, we can see the lysine is doing something. And a good point to look at what it's doing is 3 microseconds. Then you open up the next slide with the lysine, and, with the zoom on the lysine, and then you start to talk for 2 or 3 minutes about the lysine. You see what I mean? But in those figures with 8 panels, it's very difficult to see the details. So I suggest, and I think it's a good impulse, same for you, showing 3 million figures to show that you have done 3 million structures is a good idea. Just don't spend too much time on that.
Okay.
The usefulness of that figure is to impress people, not to compare information. You see what I mean? Yeah. So, and then, what was I going to say? The other thing is, regarding the occupancy estimation, looking at how you proceed, okay, I think it does make sense to spend a bit of time there. Okay? But then what you need to do is actually, I would put that between the Q390, so the explanation of Q390, and the modeling. When you go, and now we're going to do the FOCC. Is it right? Why? Because then you can justify it. You can say, see, you see what Q390 is doing. We see that basically the 2 conformations already exist to start with. And what's happening is that one conformation is disappearing and the other one is appearing. Therefore, and this is something that occurs in many other places of the protein in this cycle. So therefore, we need some tool to estimate by what degree things are appearing and disappearing. That is, we needed a way to estimate what is the occupancy in a time-dependent fashion of the different elements. And so to do so, we're going to use a methodology which we call dataset extrapolation. And then you can go into detail how to do it, okay? And why this is a good estimation of the occupancy. But make it part of the story. It's not just the technical part. It's really essential to understand how the behavior is. And then I would ask you to also have some occupancy traces.
You mean for other residue?
Or for Q390. I'm sorry, for Q390 you had it, but for some other residues. Try to, if you're going to spend so much time discussing the idea of occupancy and so on, you need to draw some conclusions from that occupancy. You know, you need to make it clear that to the audience that they have spent so much time working on, so trying to understand this relatively complex concept of extracting occupancy information from a difference map. This has to be good for something. This has to bring some important information, isn't it? Some important point to your story. If you cannot do that, I suggest that you remove it completely. Is that right? Because remember, your time is limited when you're doing the presentation. So you need to make sure that you're giving it your best, that you're telling a story that is very compelling. Okay? So yeah, that would be my point. In general, I think it's pretty good. It still needs work, but I think it's pretty good. And we need to work on the conclusions, definitely. That's something I will help you with. Maybe we can sit together, and now that he has a better overview, I think this is the time to sit down and start to think about what exactly may be happening there, isn't it? And think about perhaps extra experiments, as I mentioned. What's her name? Beijun, the new girl that is coming. She will be doing like the idea is that she does millions and millions of mutations, isn't it? So by the time she arrives, we have to have sort of a big list of mutants that we want her to be doing for the entire crack rate project, isn't it? So that would be very, very good. And I mean, if we need time response spectroscopy, if we need anything that we might need, this is the stage where all of the data is getting together. So we start to need to think about where to start to include adjacent data, isn't it? So yeah, That would be my proposal right there. So, or my suggestions to you. Okay? And as I mentioned, add UK's stuff.
Okay.
That is absolutely necessary. I'm probably not going to be there on time. Tell them to wait. Okay? Because now it's 3:30 thingy. I think surely there will be other questions. I don't know if you want to stay for a bit to give her some pointers. I'm going to be on my way, okay? But you should definitely, if not here, maybe later, try to tell him about something. Maybe, I'm sure you will have a lot of notes to definitely discuss it with him, okay? I'm going to be on my way. Thank you, guys.
Pointer.
Okay, see you later.
Anyone have questions?
为什么会有 photo cage？
为什么会有 photo cage？
什么时候多了 photo cage？
本来就有啊，
真的吗？
这是原本的计划。
你们一开始就有。
不然要怎么让它走？不然你要怎么做 time resolve 的实验？
一开始是讲 soaking 的吗？
不是啊 soaking 你把它泡进去啊，然后嘞。
我要开回来吗？还是
I think you know what to ask.
Yeah, it's fine. It's fine. Yeah.
你开着，你开着。
It's okay. I thought okay.
本来就是有 photo cage 啊。
真的假的？
不然你 time resolve 的实验就是绝大部分还是选择用照光的方式啊。因为你如果是用 substrate 跑进去，就会有那个时间的问题。
说不定 NRPS 反应，
你不知道啊？
但是 photo cage 也很麻烦。
Nice work.
Thank you.